Hello everyone, welcome to this short webinar as part of the Morrison's Net Zero series. Today we're going to be talking about soil basics, in particularly understanding soil organic matter and how to establish a soil carbon baseline for your farm and fields. We often get asked, where do I start with regards to establishing and understanding a soil baseline status, and when is the best time to start? The answer to this is simple, the sooner the better. In terms of where do you start, it's important to begin with understanding the three critical areas of soil. To bring it back to basics, we need to look at the three aspects of the soil: physical, chemical and biological. Each section of the soil poses its own unique challenges, yet organic material is relevant in all three areas. The importance of organic material in our soils can be summarised by some of the following characteristics. Improved soil structure, which is key to the physical nature of the soil. Increased water retention, reduces through flow of rainfall and runoff. As a result, soils are more resilient in dry conditions. Nutrient retention also benefits as soil erosion and leaching is minimised. Organic materials in the soil is a significant source of carbon, and it also helps promote biological activity. It is also important to consider what depletes organic material in our soils. Processes such as deep cultivation and intensive cropping, for example. We can then consider what processes allow us to increase the organic matter content of our soils. Techniques such as cover cropping and integration of organic manures. A good place to start is by getting hands-on and looking at the physical nature of your soil. The best way to do this is by getting out in the field with a spade and carry out some visual assessments. The VEST system is simple to follow and quickly allows you to assess and grade your soils. You can download a VEST score sheet and instruction sheet online from various sources, such as the link at the bottom of this slide. You can see in the example images on this slide that were taken during a VEST assessment across a farm in Lincolnshire. Using the VEST method, we were able to identify different grades of soil across the farm. See how some soils were incredibly compact and blocky in structure. This would score poorly on a VEST assessment, whilst other examples present nice, friable soils with good structure. A more advanced technique for understanding physical soil characteristics is a soil conductivity survey, which can be carried out by a third-party service provider. This process collects an accurate, high-quality mapping data set that is ideal for understanding in-field and farm-wide variability of soil types. High-density data is collected in a uniform fashion before being processed into a more familiar-looking contour map. In the example below, the red and orange areas of the map display a low soil conductivity measurement. This is usually associated with lighter, drier and free-draining soils, whereas the blue and dark green areas suggest heavier soil types with higher clay and silt content. When this service is carried out across the entire farm area, it creates a very effective visual display of soil type variability. As you can see in this example, we have a very variable landscape. Note how the soil structures compare from the different areas of the farm. The heavier soil types are prone to compaction issues and as a result, waterlogging. The lighter land to the east presents much better structure with evidence of root mass and other organic material throughout the soil profile. This is usually a good sign. We can use datasets such as soil conductivity to identify these different soil types and target them when it comes to soil sampling. Now let's take a look at how to sample and measure the soil. Again, let's start with the basics. Using a suitable sampling technique is critical. In its most crudest form, soil sampling is often carried out using the whole field method. This is easy to do by yourself, and there is useful guidance available online. However, whole field sampling has many drawbacks, and you should really consider your sampling methodology depending on the type of analysis you are looking to carry out. When it comes to soil sampling, we strongly advocate the use of GPS technology and automated sample extraction. Specialist machinery, like in the example shown here, allows for consistent sample extraction time after time, removing the risk of human error. Each sample extracts the same amount of soil from exactly the same sample depth down the soil profile. When we couple this with GPS logging hardware, it allows us to identify where each and every soil sample has come from and allows for highly accurate repeatability in years to come when it is time to resample. One of the most critical, yet often overlooked aspects of collecting a soil sample is understanding sample depth. Depending on what you are wanting to analyse your soils for, this is very important. For the purpose of soil organic matter assessment, in particular for understanding soil organic carbon, we recommend a minimum sample depth of 30 centimetres, which is in line with guidance set out by the IPCC. It is also advantageous to be able to understand how levels of organic material change throughout the soil profile. By having the capability to measure at depth, it offers an excellent insight into effective soil management over time. It gives us a much more stable measurement, as these areas of the soil profile are less likely to be directly influenced or potentially skewed by certain farming processes. It represents a truer growth of organic content within our soils over time. Now that we are confident that we have collected a robust, accurate and representative sample for lab analysis, we can now turn our attention to the analytical options on offer. Choosing the right lab assessment for your particular situation is key, as you can soon spend a lot of money on lab analysis, but risk oversaturating yourself with information in return. If you are unsure on what specific lab analysis you think best suits your needs, any good service provider will be able to demonstrate and advise on the options you have. Once we've received our analysis back from the labs, there are a few things for you to consider when looking at the results. Are your soils deficient? Are they above the target recommendation for your particular scenario? Is your soil variable across the farm? Is your soil variable across an individual field? Do the results correlate with your existing knowledge of the land or any known characteristics or previous management decisions? Once you have answered these questions and have explored why, you then have the building blocks to develop your management plans moving forward. As you can see with the example report here, we can easily identify our priorities with regards to soil nutrition. We have also identified that our organic matter level is considered slightly low. Let's look at this in a little more detail and find out how this forms the basis for understanding soil organic carbon. Through commercial laboratory analysis, there are two main forms of organic matter assessment. The most traditional and historically more widely used method is often the loss on ignition test. In its simplest form, the loss on ignition test is where we heat up the soil sample and it burns off any water or organic content within the soil. The resulting loss of mass all contributes to the LOI result. Although this form of analysis is cost effective, it does have its drawbacks and is not suitable for all situations, such as soils with high clay content and calcareous soils. The Dumas methodology, also known as dry combustion, is a similar concept. However, it allows for the measurement of the different gases released by the soil upon combustion. This is done using infrared spectrometry. This method offers a true carbon measurement, allowing us to differentiate between total and organic carbon content. This is then correlated into organic matter. If you are interested in measuring soil organic matter for the purposes of understanding soil carbon, ensuring that your soils are analysed using the Dumas method is critical. When analysing soil organic matter for purposes of understanding soil carbon, we've already identified two critical requirements. 1. Sample depth and provenance. 2. Ensuring that we use the Dumas dry combustion method. The third aspect is assessing soil bulk density. In order to calculate a carbon stock baseline, the formula also requires a soil bulk density metric. Again, in its simplest form, bulk density is an assessment of the amount of soil within a given area. Soil bulk density is expressed in a metric of grams per centimetre cubed. Typically, lower bulk density values are more desirable as it indicates less soil compaction and more porosity within the soil structure. Taking a bulk density measurement can be tricky for many reasons, but there are a couple of options here. Many standard lab reports that have processed a soil organic carbon test will use an assumed bulk density value if one hasn't been provided prior to be factored into a carbon stock calculation. Another option is a lab-derived bulk density measurement using a broken soil method. This is technically a particle density assessment as it does omit things such as stone content. However, it is potentially more consistent and less subjective than a traditional bulk density assessment. The true bulk density methodology requires a known volume extraction from the soil profile. This process is manually intensive, tricky to carry out on consistently stony soil, and is more expensive to process in the laboratory. However, it can offer the most accurate bulk density measurement. Once you have obtained a bulk density measurement, you now have the tools to begin calculating your basic soil carbon stock baseline. Here you can see an example calculation. In this instance, we had a sample depth of 30 centimetres. We measured our bulk density at 1.3 grams per cubic centimetre, and we have an organic carbon analysis of 3.2%. As a result, we have a base calculation here of 124.8 tonnes of organic carbon per hectare. This can then be translated into an estimated CO2 equivalent simply by using the simple formula below. Hopefully this short presentation has informed you on where you can begin to start assessing your soils for organic matter content and as a result a soil carbon baseline. I like to finish with this image as it is a great reminder to us how different our soils can be depending on our particular geography and land use. The more you can understand the soils on your farm for your unique situation, the better you will become at managing them. There isn't a one-size-fits-all approach, so find what works best for you. Thank you for listening. Should anyone want to discuss any of the topics within this presentation further, please feel free to get in touch with us using these contact details. Thank you.